All right, welcome everybody to session C, curriculum, undergraduate, postgraduate, and doctoral. So we have a jam-packed session, and this is what's standing between us and dinner. So presenters, 9 to 10 minutes, and then we have kind of groups of presentations, and we'll take questions after similarly themed presentations. So I will let Charles get started.
All right, good afternoon, everyone. I will be talking to you about simplifying slope stability, what should be taught at the undergraduate level. And this is basically a reflection on how we decided what we would teach in our undergraduate course on slope stability. So just some context, we have 3 geotechnical modules. The first is engineering geology, and then there's a soil mechanics module, and then the second one where slope stability is taught is more applications. I guess you could term it geotechnical engineering. So just an overview of the paper, which I will not be presenting on entirety in this presentation. The first section is a review of slope stability content presented in common English language textbooks. And then there's a section on taking it outside. So there's a brief write-up of teaching activities that we include in the module that are designed to encourage students to learn outside the classroom. So how do we basically force them to engage with the material that we give them? Where my presentation will start today is on more than semantics, so discussion of semantic gravity and semantic density. And these are concepts that we use in a lot of our modules or our thinking about teaching at Stellenbosch University, the semantic plane, and how these concepts influence what we teach. And then I will talk about the case studies, visual case studies that we use, and then an intuitive slope stability exercise, which we use to develop slope stability language, and then constrained theoretical models and general theoretical models. Okay, so this is a, what we call this, it's a graph where we have got 4 quadrants. And the first quadrant, is where we use informal language for very specific examples. And we tend to introduce our context in this quadrant. And then the second quadrant is where we're still using informal language, but we're trying to generalize the concepts from very specific examples. The third quadrant is where we're starting to map informal language to formal language or symbolic logic, so numbers, equations. And in that bottom quadrant, we're still looking at specific examples, so equations that have very limited use. And then the fourth quadrant at the top there is where we're still using formal language and symbolic logic, but we're generalizing the equations to equations that can be used for a number of different cases. And there's obviously a progression through these quadrants, but there's also a linking back that takes place in the courses. And you can read up more about this in the paper. So just to summarize, excite and motivate students. In the bottom, the top, develop slope stability language, calculations for specific failure mechanisms, and then calculations for general failure mechanisms at the top there. Okay, so when it comes to case studies, there are 2 types of case studies that we can identify in literature. The first is what we call affective. And the Trenching and Excavation Safety Task Force is a great LinkedIn group to get examples of excavations that go badly. And a lot of civil engineers will excavate or will dig a hole at some point in their careers. So it's very important to highlight to students the risks associated with that. So that's where it's just case studies to excite and motivate students. And then we also have case studies in the course that are cognitive. So cognitive case studies are ones where we can illustrate, develop, and apply theoretical models. So these need to be fairly simple case studies where we can actually use the equations that we are teaching the students and show that they actually can work to make predictions. Now, we then move on to this intuitive slope stability exercise, which is an exercise to try and get students to engage with the language of slope stability. So what happens in this exercise is that students work as groups, and they are presented with a number of examples like those at the top there. So some have a phreatic surface, some don't. There's different strengths. And the students develop rules to say, okay, if the friction angle is this, then it's going to be more stable. So they use different terms. And here are just two examples of the heuristics or rules that are developed. So some of them are nice and neat, and they've actually got some decent terms used. The ones at the bottom is very informal language, and we then take those terms and we actually map them in the classroom to say, okay, you've said shorter seepage. And we sort of say, okay, what do you mean by shorter seepage? And they say, okay, when the phreatic surface is lower or when it's higher, it influences slope stability. So just to give you a flavor of what this involves, I've got two examples here, A and B, and I'll give you a few moments and I'll ask you which you think is more stable. So if you think A is more stable, you can put up your hand now. So if you think A is more stable, or if you think B is more stable, A. Okay, so you should pretty quickly realize that A is going to be more stable because B has got a 90-degree slope. This one is a little bit harder. So if you think A is more stable, and if you think B is more stable, okay, so there were more hands for A. So A is indeed more stable. The friction angle there is 35, and the slope is 30 degrees. So tan, you can just use the tans of the slope and the angle and the friction angle to get that. The second one has a phreatic surface, which makes it a bit difficult. But there, the friction angle is lower than the slope, so it's obviously going to be unstable. So these are the types of scenarios that students have to evaluate. And this is a really useful exercise to map an informal understanding of slope stability concepts to the more formal concepts that we then cover in, firstly, constrained theoretical models. So here, the specific failure mechanisms that are covered are undrained vertical cuttings. So there's one equation that works for vertical cuttings. It can't really be used elsewhere. Then drained infinite slopes, and undrained rotational slides. And in the content, we both derive the equations, and then we also use two case studies to illustrate these concepts. So the drained infinite slopes, where we live, there are a lot of mountains around us, and after heavy rainfall, we often get these infinite slips along the mountain slides and sides, and that can be used just with very simple equations to illustrate how the changing seepage direction influences stability. The second example that we use for undrained rotational slides, a mine in Botswana decided to build a causeway over a tailings deposit, and so they deposited that 14-meter high embankment in about a month. And it actually, the embankment stayed stable, but the stuff was displacing into the underlying tailings, and we could predict the height at which this would be failure would occur just by assuming that the material was undrained, and there's CPTU results to estimate those parameters, and then the calculations for general failure mechanisms. The Swedish method, Bishop method, these are all fairly common. Derivation and case studies. For the Swedish method, we use a case study of an industrial waste facility that is lined. And for the Bishop method, we use an embankment dam that failed because the drains got blocked. And just these case studies are available, and they are written up with 5 headings: the observed performance, so what, where, and what happened; the site investigation, what information is available; The third is the analyzed mechanism, calculations to inform decision. And then we also give some teaching suggestions, how to use the case studies, and then photos and videos and references. And this is just an example of the one where they built the embankment over the tailings, the information that is available. And if you email me, I can share those with you. And then just a parting thought. I found this illustration on the internet, and I think we need to remember that the behavior of soils and sands is actually very complicated, and we need to help our students get there, even if it's slowly. Thank you.
So we have another presentation on slopes, so we're going to take questions after these two are done. So next up is Vittoria.
Good afternoon, everybody. I'm Vittoria Capobianco from Norwegian Geotechnical Institute. You may wonder why I'm standing here talking with you, since I'm not teaching at university. But today I want to present to you this course that we developed together with other universities within a partnership project. And some of the co-authors, at least one that I know of, is also part of this technical committee. So let me introduce a little bit GEOMME. As I said, it's a partnership project among Norway, Japan, and Korea on climate-driven geohazard mitigation, management, and education. So it's committed to advancing excellence in education and research on these topics, and it has three main objectives. The first is to educate, prepare students, future practitioners on these topics. The second is about exchange, promote research collaboration and mobility. And the third is to develop institutional linkages for future collaborations. As you can see from the list of partners here, we have two partners from each of the three countries. And one is a research institute, and another one is an academic partner. And the project is funded by the Research Council of Norway. So how GEOMME works? The activities in GEOMME gravitate around four areas for collective scientific advancement that we called progression domains, which means that every year the partners of the project are focusing on a specific thematic area for collaboration that has been identified based on the knowledge gaps existing in research and education. So the main product or the main activity that is done by this GEOMME partnership is to organize on rotation each year a 2-week intensive course with students from the three different countries and the partners on this specific progression domain. And here you can see the timeline. We are at the 4th year of the project, and since 2022 we had the course in Norway, another one held in, you can see my cursor? No, you can't. But in 2023 we had it in Japan, in 2024 in South Korea, and this year actually it wrapped up last week in exceptionally was held in Italy at University of Florence. And I will mostly talk about the results of this course that was held this year on sustainable approaches for landslide risk reduction and soil improvement. But in the paper you can find also the contents from last year edition, which was also about landslide prediction, mitigation, and management of landslides and debris flows. So the course is always structured in the same way, and each year the responsible of the course defines the 4 main learning objectives that will need to be addressed. And we have a pre-course online module where we provide background and introductory materials to the students that will participate to the course 1 month prior to the start of the course, to make a basic level of knowledge among all the students, because they come also from slightly different backgrounds. And then we have 2 weeks of course. The first week is focused on in-class lectures. So we have a morning session with theoretical learning. In the afternoon we have practical exercises. We do applications, use software tools, where we do exercises on topics that we were introduced in the morning. And the second week we have an excursion module where we have a full week of field visits, possibly to sites that were introduced as a case studies during the first week of the course. And we also provide a printed excursion guide with extra technical description of the case study site and reference materials, so the students and also the partners can look at it after the end of the course. Here are some numbers from this year course, but more or less the numbers were the same also in the previous years. We have about 20 students. We have an average of 11 lecturers. Most of them are the partners of the project, but we also have invited lecturers or speakers. This year was extremely international because we also welcomed participation from students from universities in Italy. And this is the gender balance. With regards to background, the course is primarily led by people that work in the geotechnical engineering field with 75% of representation. Here you see a word cloud that is sourced from ResearchGate and from the keywords of each of the lecturers. So you can see there is a lot about slope stability, risk assessment, and landslides, of course. But then, especially this year, which was a little bit more interdisciplinary, a quarter of the lecturers were also coming from a different background, like forest engineering, environmental engineering, and engineering geology. Regarding the students' background, we had most of the students coming from civil engineering or geoengineering faculties, but also geoscience like geology or forestry and others. So here is a textbook-based presentation, but basically it's to show you a little bit the structure of the first week of the course. And on the right-hand side, you can see the pictures from the class. In bold, you can see the topics that we touched every day in the first week. So we started broad with climate change and landslide risk management in a changing climate, introducing new concepts like nature-based solutions, integrated approaches. Then the second day was focused mostly on the quantification and modeling of vegetation reinforcement in slope stability with examples of modelings and also associated uncertainties. Then we moved on to some practical cases like landslide risk mitigation options, both structural, non-structural, or conventional like engineered structures, and also more nature-based type of mitigation options. The fourth day was dedicated to the role of protection forests and how to quantify forest root reinforcement for landslide risk reduction. And the last day was dedicated to bio-based and bio-inspired solutions for ground improvement and latest research advancement in the field of biocementation or biopolymers and such. So here is a result from the survey that we ask both students and participants, also lecturers, to fill at the end of the week of the course. And we asked which element, in their opinion, contributed most to their learning. Most of them, or at least in the same number, we can see that both lectures, like traditional in-front lectures, represented the main element of learning, followed by interdisciplinarity. So the interdisciplinarity that was brought from bringing lecturers from different fields was highly appreciated, and also followed by practical exercises at the end of each day, which reinforced the knowledge gained during the mornings. Here are some pictures from the second week of the excursion. You can see that, for example, on the left-hand side, we were at the case study site where the students could see a landslide stabilization work that was done after a landslide occurred on a mountain road, and then they did some hybrid solution using mini piles together with live crib walls and vegetation cuttings. And you can see an extract from the excursion guide where the students could bring on field, and while they were explaining, the local guide was explaining the solution, they could also see the technical solutions that were modeled in the text, etc., in a more in the geotechnical model. On the right-hand side, you can see a demonstration of a field route pull-out tests, where also the students were somehow asked, or they volunteered to do some field route pull-out tests. This is also coming from the survey that we sent to the students at the end of the course. We asked to what extent their understanding has improved on these topics, or on these topics, and we asked to rank from 0, same as before, to 5, which means greatly improved. And not surprisingly, of course, since one of our learning objectives was to bring in this innovative aspect of including root reinforcement and vegetation effects on slope stability and nature-based, bio-based solutions, was one of the main learning outcomes, followed also by some other aspects that are facing also landslide experts in these days. For example, the effect of forest fires on landslide triggering and slope stability, but also it was highly ranked the interdisciplinary aspect of the course. Here is a word cloud that summarizes the topics that they would like to explore further in the future. And as you can see as well, like wildfires come quite often, or biogeotechnics a little bit more in general. And the main takeaways are that specifically, we have many commented that they appreciated to gain new insights from diverse approaches from different countries to similar challenges. And this allowed them to gain an international perspective, also understanding the variations between guidelines in different regions, in different countries. But also they appreciated talking with people from different disciplines to gain new perspectives, and some comments for improvement that we received, which I can skip. And yeah, I would like to acknowledge all the lecturers and the local guides that allowed us to make this course a success. And yeah, just look at our paper if you have more curiosity about it, and if you want, you can just reach me out. Thank you.
We have time for a question or two from Charles or Victoria, and if you have a question, just let us know who it's for.
In my mind, we heard the edges of the spectrum, the classical slope stability, that was Charles' presentation, and this, in my mind, these are futuristic things, and so I would like from you a comment on how Charles perhaps can infuse his presentation with something of this. I don't know if I'm asking for something too big.
No, maybe, I mean, I really liked his presentation, actually. It's a bit more fundamental type of teaching. Our type of teaching was really practical. So we also did some LEM slope stability analysis using an open access software with the students. And it was really practical. And some of the students did not have the background before. So we had to guide them to do the exercise. I don't know, we didn't have a lot of time because it was just an afternoon session of a couple of hours for exercise, but it was really nice also to see how they tried to learn a new software and how they tried to understand how this slope stability analysis works, and also they were able also to see in practice this afterwards, because we did an exercise which was then visited in the second week. So they had to think a little bit first theoretically, and then they looked at it practically from a more practical point of view. I don't know if I answered your question and if I gave some inputs, but yeah, that was our experience.
Okay, thank you very much. We are going to go on to a next set of 3 presentations, and then we'll take questions after those. So the first is Geotechnical Engineering Knowledge Base Needed for Improvement of Mine Tailings Safety.
So good afternoon. everyone. I will present the work and paper and thoughts prepared by me and colleagues Burecic Safran from Zagreb University and Professor Znidarcic from University of Colorado in USA. So first of all, what was our motivation for this paper? From the real world, we are aware that due to increased quantities of mine waste all over the world, there is already a lot of tailings dams also, more than 10,000. And it is expected that the number and size and the complexity of these tailings storage facilities will increase further in future. What is not good is that failure rate was unacceptably high. It is something like 100 times more than for water dams. So this is something which is not good and should be changed. And even worse is that the causes could be foreseen and prevented if the geotechnical engineering knowledge was applied. So it was already documented something around 25 years ago by ICOLT based on the case records of failures. And then they came to conclusion that just the adequate and enforced application of available engineering technology to tailings storage facilities must be achieved and will improve the whole situation. So the problem was recognized already in the past. And we can ask ourselves what is so complicated with tailings storage facilities. First of all, these are very large dams, hybrid facilities, mainly built by mining and civil engineers, but other disciplines are also participating. Then there you have tailings materials that possess unique behavior. This is different than soil or rock material. They are very often built in remote areas and in harsh environments, but still they have to be designed and to be safe for a very long lifetime. In some countries, it is several hundreds of years. And the mining industry recognized this problem, and in 2020, this standard appeared. And one of the things that they have concluded is that better management of human resources within mining industry could be the possible solution, because in this document, the roles and responsibilities of engineers working at tailings facilities are somehow defined. But all over the world, we can see that we have less lack of interest for studying mining engineering or mineral metal processing or engineering in general. At the end, it causes also the shortage of specialized tailings engineers globally. So we can see that the problem actually still exists. And working at the university, we could ask ourselves what would be then the responsibility and the role of higher education institutions, and how can we help to this industry to attract younger generations to find their perspective in such a challenging industry, and interesting in fact, and to improve knowledge. In order to improve the safety of these dams. And I will just talk about one aspect of this design that is connected to geotechnical engineering and geotechnical modules at our universities. And then I had also my personal motivation from the lecture room, because 2 years ago we started one Erasmus joint master program where the heterogeneity of student population was substantial. They are coming from 11 countries, and their background was different. They were mainly studying mining or metallurgy and mineral processing. So their knowledge about geotechnical engineering, water management, environmental geotechnics, all the things related to geotechnics was just basic, if any. Some of them didn't even been taught anything from that. Still, it was quite demanding, obviously, for the lecturer to provide the lectures for such a heterogeneous student population. But still, we have performed survey, and at the beginning, before listening to this course, they judged this environmental geotechnics courses as extremely important, half of them. And afterwards, at the end of the semester, it even increased for 25%. So 3/4 of them judged this as extremely important. So it is somehow promising that we can do something to improve the practice as well, that we will be able to get some students into tailings management. And then returning back, what we can do as professors, considering the fact that we have so many problems, they are just here written in red letters, but you can see other things also within the article. And then we get to this idea, general idea, to offer inverted TSF triangle. It is obviously in line with Berland's geotechnical triangle, but what is different? So for tailings dams, we have put it two things in the equal position. This is the origin and characterization of tailings, and water management and seepage control. Then at the bottom you have engineering behavior and modeling. In the middle is obviously TSF management or practical application. And all of these things are connected into one cloud that should cover sustainability and environmental soundness. This is something which is for the mining industry very, very important. And beside this general TSF triangle as a proposal, our proposal, we have developed some initial informative graphics that will cover just one of these major pillars related to origin and characterization of tailings. And our idea is that we can offer something like that in our environmental geotechnics or mining geotechnics or geotechnical departments to students to introduce to them man-made materials and to critically examine some commonly accepted concepts from soil mechanics, whether they can be applied or how they can be applied to tailings materials. So the first one is related to the origin of soils and tailings, and this is our informative graphics that is offered. And in fact, what is the message behind, which we would like to transfer to our students, is that although tailings materials have the same origin like soils, that is parent rock material, due to different processes and duration of processes in their lifetime. So for soils, there are natural processes, very slow. And in tailings management, you have industrial processes that are much faster, rapid, and also they are using a lot of chemicals. Some of chemicals are even very strong. So although we have the same parent material, at the end, we cannot say that soils and tailings are the same. And you can also see at the bottom of these graphics that even if we compare terminology, we can see the differences, because in tailings engineering, they are just using terms slime for fine-grained materials and sand for coarse-grained materials. Gravel size, they do not exist there. And also they are covering a little bit different grain sizes of materials. The next one is related to the classification of soils and tailings, and what we can see is that in tailings engineering they are using the same methods. So they will get grain size curves, and they will obtain Atterberg limits. But if we compare the grain size analysis and the groups that are classification that is offered for tailings in relation to soils, you can see from the grain size analysis that most of the tailings are in much narrower range of grain size distributions, and there is a practical reason of that, because due to afterwards mineral processing methods, they have to crash the original rock materials to very fine particles to be successful in the further processing. And there is even much higher difference if we compare the plasticity chart. And you can see there that in tailings management, you have 5 different groups, but they do not follow the same logic like we are doing in soil mechanics. So A line does not divide cohesive and not cohesive, or plastic and not plastic materials. So some of materials they have a fine, the grain size distribution belongs to the fine grain soils. In fact, actually, you are getting some different conclusions if you are looking into this plasticity chart. And moreover, for the tailings, sometimes, very often, there is a need for some additional methods to divide, for example, something which will behave like clay-like tailings from, for example, the same grain size distribution could be rock floor that is completely different material, considering plasticity. And the third informative graphics is related to soils and tailings properties. And again, you can see that the same methods are used, whether we are talking on laboratory or in situ testings. But although the same methods are used, the properties may differ significantly, because tailings, the properties of tailings are dependent on the parent rock material, parent ore. Then on the mineral processing treatment, as I already told you, there are physical, chemical, biological methods. Sometimes they are using strong chemicals. And then alteration afterwards during the transportation and deposition in tailing storage facilities. Sampling is much more difficult for tailings than for soils. And if you are considering also that there is a temporal and spatial variability also there present, then to obtain the design parameter is getting to be really, really difficult in tailings. Considering field testing, they can use correlations obtained for the soil materials. But as we already heard, this is not the same. We do not have, at least I do not know. Okay, okay. I'm going then to the conclusions. So to fulfill the demands of the industry, we are proposing this TSF triangle. We started to prepare the materials, what could be used as a teaching materials, and we just tackled one of the pillars. And the next step would be to convey again the survey to see whether with this we have increased the interest among students and what are their thoughts. And if this general concept is acceptable and if the survey results would be positive, then there is a lot of work to be done in future. I've mentioned here some of them because we have just tackled this left-hand side pillar, and there is a lot of other things that should be covered. In that sense, I would like to have your opinions and suggestions, and with this, I thank you for your attention.
Thank you very much. Our next speaker is Talia de la Silva Burke, and she will talk about linking theory to practice, the semantic wave in postgraduate critical state soil mechanics course.
Right, so while my presentation's loading, so I'm also from Stellenbosch University, same as Charles, and I'm going to be speaking to you today about my experience of putting together a postgraduate critical state soil mechanics course. And the reason I've been grouped together with the mining talks is that I've used our local context and the mining industry specifically as a practical implication of that. So this is the course we had. We have a critical state soil mechanics postgraduate course for master's students. And this was a new course that was presented for the first time in 2024. It was a module that I took over, and I developed the material for this. And our postgraduate courses run as blocks. So we have a 5-day block week, so I had 4 days of lectures, and then there's 1 day where the students can work on the assignments for the course. And the course had 2 main components. So I looked at soil behavior in the laboratory, or critical state soil mechanics in the laboratory, and soil behavior in the field, which was 1 day. And how the assessment worked is there was a pre-course reflection based on some limited pre-reading, which counted 5%, and then the lab behavior assignment, which was 35%, and then the field behavior assignment, which was the majority of the course. So why did we decide to include critical state soil mechanics in our postgraduate curriculum? It wasn't there before. From my personal point of view, it's kind of a beautiful and thorough encapsulation of soil behavior. It explains why soil as a particulate material responds to void ratio and effective stress, and you can get drained and undrained parts, and it just brings everything together really nicely. More pragmatically, we see a lot more use of advanced numerical modeling and constitutive models in industry. So students need to be able to understand what they're doing when they're clicking the buttons and putting in the parameters for that. And finally, in our local context, so in South Africa, critical state soil mechanics is used increasingly being used in the stability assessment of tailing storage facilities. So we have a significant number of TSFs in South Africa, and these tend to be managed by the geotechnical engineers, not the mining engineers. And critical state soil mechanics is used to determine the contractive potential of the material, which leads to understanding if that static liquefaction failure is likely or not. Okay, so the model that we used, or that we presented, was the Norsand critical state soil mechanics model, and this is with the development of the state parameter as presented by Jeffries, and the course material was primarily based on the course that was presented by Jeffries and Shuttle, which is linked there. It was a Vancouver Geotechnical Society workshop, and they had all the notes and all the slides, and it was a fabulous resource. And if you present anything on critical state soil mechanics, go look at it, and it's all there in PowerPoint. So it was a really great resource. So if you're not familiar with the state parameter, this is separate to the critical state parameters, which is your lambda and your the slope of the critical state line. So the state parameter is a measure of how far away from the critical state a soil is, assuming a constant mean effective stress. So we can have, at the same void ratio, we can have a negative state parameter, if we have a low mean effective stress or a positive state parameter. And the reason that this is important in our local context and the tailings applications is that a positive state parameter is indicative of a loose or contractive material where you are potentially likely to get an undrained static liquefaction failure. And a negative parameter is a dense or dilative material, which we're happy with. It's going to behave drained. So the overview of the course, so the aim was in the laboratory was to look at how we use triaxial tests to determine the critical state soil parameters and to verify the model that we have. And then in the field section was looking at the use of cone penetration test data to estimate what the in situ state parameter was and to predict liquefaction. And the two main things that I wanted to kind of bring out from my experience of putting this course together was the very deliberate effort to link theory and practice that was made throughout the course. And then the results of a slope stability round-robin comparison that I had the students do as part of their assignment. So the first part is linking theory to practice. So you would have seen Charles presented the semantic plane. Another tool that we use is the semantic wave. And this is where we go from high semantic density, so abstract, very technical, and then we go down into concrete, simple, and then we go back up again into abstract and complex. And our goal is to intentionally cycle up and down through these waves so that students can keep linking the theoretical knowledge to the concrete application. So the course structure is nothing revolutionary. It's critical state soil mechanics. So it's all the basic critical state concepts, then elasticity and plasticity and the state boundary surface, and then on the third day, the North Sand model. And then each day there was a extensive tutorial time based on the implementation of that theoretical knowledge into processing laboratory data. So they got real laboratory data, and then they had to process it and determine the critical state parameters of this material in class. And then the fourth day, the same thing. They presented the CPTU testing, and they needed to get the state parameter. So this is just a very typical schedule. Now, if we transfer this into kind of the semantic wave concept, we have the lectures at the top with all the theoretical knowledge and the tutorials at the bottom with all the kind of concrete practical applications. You can also think of it in the more passive active learning style. So the top is the more passive lectures and the bottom is the active and the tutorials. And you can see for the first 3 days, we start at the top and then we go down, and then the next day we start at the top and then we go down, and we go down again. And then with the field testing, there's a bit of a break. It's a slight, it's not continuous in terms of, we now approach the problem from a slightly different angle, so we start, again, it's not a continuous wave. But when we looked at this, when we deliberately used this model, we wanted to we needed to structure things in between that to make sure that we properly took the students on that journey and didn't just go up, down, up, down. So we added in deliberate tools or extra things in between to help the students do that. So some things were examples were lectures on the laboratory procedures or specifications of the laboratory tests for critical state testing, demonstrations of stress paths that you would follow during tests on the different models, the use of physical models, so I 3D printed a CAM-clay model, as well as virtual models, the models from Innsbruck that they've got online and that students can play with, and then demonstrations. But then we still felt we wanted to add one more thing, and what we wanted is that students really start with contextual understanding. So we added in something that they would start in the real world, in the concrete. So they start with a case study activity, and at the end, do a review of that case study so that all this theoretical knowledge about critical state soil mechanics, I'm not sure about you, but when I was taught it, it was like way pie in the sky, and I didn't use it for 10 years afterwards. So I wanted to really draw into how they're going to use it. So there was this case study activity, and for this, the students were put into groups, and they had to review each group had to review one case study. They were just given the name of the case study, and they had to go and find information on why it failed, and then give a presentation to the class. This was all completely self-study. I didn't do anything for this. And this was right at the beginning, so they were given the case studies the week before, and then at the start of the course, they came together and then did a presentation on it. At the end of the course, again, they had to reflect on that case study and say, well, how does their critical state knowledge, now what they've learned, reflect on that case study? And this was really helpful for me as a lecturer to, like, as I was presenting the course, be like, oh, remember that thing that you said? This is how it links up. And they really had ownership of that. Okay, so just some reflections. It was a helpful framework to think strategically. I'll just go very briefly through the second thing, which I wanted to say was the slope stability round-robin comparison. Now, this was really interesting to me because I gave the students a paper round-robin that they had to replicate for their assignment. So they had to take their knowledge and replicate this round-robin slope stability analysis and analyze the data. And they were instructed to use a specific screening tool and to do north sand element simulations, and then to determine the factor of safety and the phreatic surface at failure. And this was intended as the primary integration of the course knowledge. And there was a huge variation in the results that the students submitted. And this was very surprising to me. The variation came because of the ways that they selected the state parameter, the accuracy of the north sand element simulations, and the appropriate ability to specify limit equilibrium module, not even finite element, just limit equilibrium. And this was surprising to me. I think when we look at round-robin exercises, we often say, oh, it's because people didn't give enough attention to it. They just did it as a little bit of fun. But this was a case where students had incentive to participate. They'd been taught all the key elements. They accounted 60% of their mark. And they had the paper with all the results of everybody else that had submitted to compare their answers to, and they still didn't do that. So this highlights the need for careful model interpretation and improved instruction, and specifically how we teach students how to translate their theoretical knowledge into the more practical. All right, so conclusion. So critical state's a valuable part of postgraduate geotechnical engineering understanding. I think all of us would agree with that, hopefully. Demonstration of practical relevance is key to enhance student engagement, especially if it's connected to the local context. And we need to ensure that students are aware of appropriate ways to incorporate critical state soil mechanics into numerical and limit equilibrium models. Thank you very much.
In this section, a 3-year multidisciplinary project training in mining engineering to build bridges across the disciplines. And just a reminder to the instructor, or to the presenters, I will show you when you have 2 minutes left and 1 minute left, and when I stand up, then you're at the 10-minute mark. Thank you.
Thank you to give me this opportunity to share our experience in projects in mining engineering. So we are using this type of project approach for many years now, so it's nice to share our feedback with you. So our mining engineering studies are part of the Faculty of Engineering in the University of Mons. And the motto of the faculty is "End up, create and create yourself." This approach aims to provide future engineers with a high level of technical education It's the create side of the arrow, meaning that we start with very basic knowledge in engineering sciences, and progressively, during their 5 years of studies, they move to more specialized courses. Meanwhile, create yourself means that we encourage them to question their future career by means of different activities like international mobilities or internships. Of course, this strategy also applies to mining engineering, and this is a specialization that starts from the 3rd year of the bachelor degree. So at this level, they only start to have their first courses in geosciences, like rock mechanics, for instance. And so progressively, we move with them from fundamental courses to more specialized ones. And rapidly, we introduced a project approach in the 3rd bachelor degree. And for the create yourself part, we focus on transversal skills like teamwork, autonomy, professional contact with the industry. What I would like to highlight today is the continuity that we use in this project approach. In fact, the key is what we name a mining engineering problem. This project starts in the 3rd year of the bachelor degree with a geomechanics project, and the students continue with the same project along different courses. I mean, in the 1st year of the master degree, they have design and construction of workings and stability analysis. And then in the 2nd year of the master degree, they continue with a mine planning point of view, always on the same mining engineering problem. So to illustrate this, I'm going to show you some examples. And the first one is the project that we started this year with the bachelor students. It is around a research project that is named the Einstein Telescope. It's a very big research project involving teams in Germany, Belgium, and the Netherlands. And the aim of this project is to develop an infrastructure for studying gravitational forces. So not rock mechanics nor mining. But this infrastructure involves the creation of 3 tunnels. Each one will be 10 kilometers long. So it's a very interesting project, and part of our team is involved in some part of this project. So it was an amazing opportunity for students to be really involved in a current challenge in terms of research. And the first challenge for them was to look for rock materials to test. So this was done in the geomechanics project. First, they had to understand what is behind the Einstein telescopes in terms of underground works. And then they had to characterize the rock materials in place. So they had access to the core workshop to see how it looks, but they could not sample there. So the first exercise was geology, because they had to see the maps, to go and look for outcrops in order to characterize the rock mass and to collect samples. So all the figures that you see there is taken from the students' report. I did not modify them. So it's just to show you the kind of things they are doing in terms of geological mapping, in terms of rock mass characterization and analysis. And then with the sample they collect, they decide of the experimental program, proceed to the test and analyze them. So this is what we do in the geomechanics project. Next year, they will continue with the design of the tunnels, the computation for stability, and so on. A second example is the extension of a quarry. It is a much more classical mining engineering problem that offers a lot of opportunities. In terms of geomechanics projects, it's more or less the same as I explained previously. Quarries are very nice opportunities to go to the field, to see outcrops and to collect samples. And then this slide is more suited to illustrate slope design and stabilities, because in the first year of the master, they continue with the constitutive laws that developed to make a stability analysis of one part of the quarry. Here it is a specific example by means of numerical modeling of the wall that was separating two different quarries. And this issue with a wall brings me to a kind of project that students perform during the second master, in which they have to propose a mine planning for a specific site. And so this wall was a big challenge because two operators had to share their production depending on the quality of the rock. So this example of mine plannings are performed with SURPAC, so it's a very powerful tool for mine analysis, and it was even continued as a master thesis. I have many other examples to share with you, just maybe a last one because it is nice. It's almost time for a drink. One particular project was the creation of a new wine cellar in a rock mass. So the picture shows that there is already something existing. It was a very exciting project for students, also for academics, because we had the opportunity to taste wine at the end. So everybody was happy with that. And the pictures below show you the type of proposal that students made after their investigation in terms of design and construction of works. And on the right side, the stability analysis that they performed with finite elements. Now, let's speak about the lessons that we learned from this project approach. And the first lesson is really the core of our paper, is that this problem-oriented vision allows us to create bridges across the disciplines. If I come back to the sketch that I showed previously, now I insist more on the courses that are given, the disciplines. And all along those courses, those projects, we have geology, we have engineering geology, we have rock mechanics and mining sciences. So it's a very good opportunity to become more multidisciplinary and more transversal in our approach of teaching. It develops also a variety of skills because students work in laboratory and in the field. They achieve experimental work, but also modeling. And we hope that theoretical courses become much more clearer once they apply their knowledge. We also encourage them to go beyond the course material because often, mainly for the early stages of the projects, we need flipped classroom. And in terms of transversal skills also, we develop team spirit, we develop autonomy, and also the collaboration with our industrial partners that always welcome us on their sites. For preparing this talk, we thought it was also useful to collect the feelings from the students about this project approach. And we make a poll with the Master 1 students who have already part of the experience. And the feedback is very positive globally. You see a lot of green on this figure. The main strengths are similar to what academics and scientists identified. In addition, the students promote constructive feedback because I have to say that the team is really involved in the project and we spend a lot of time in terms of formative assessment, so it's very positive to have their positive feedback as well on this. However, some challenges are identified and mainly time management. Some students really have difficulties to face that. Some other challenges like academic literature or mastering software, we are trying to find solutions for that by developing tutorials or introducing bibliographic courses. So, as a take-home message, I would say that this multidisciplinary project approach really plays an important role in forming geology and mining engineers year after year. And I would like to thank all the partners. First, I wrote warmest thanks. I would say hot thanks, because everybody is really hot today. So thanks to the team, because I cannot do this alone. It's really a teamwork. Thanks to professionals like my friend Bertrand, who welcomed us in his quarry. And thanks to the students who participated to the poll and gave us their feedback. Thank you.
So in the interest of time, we're going to hold questions. So if you have questions for any of these three presenters, please ask them at dinner tonight. So we're going to move on to the next group of two presentations. The first is an industry perspective on geotechnical engineering education and a learning approach.
My name is Hilary Shields. I'm presenting a paper written by myself and my colleagues, Dr. Yi Yap, Cyrus Toms, and Taryn Chalmers, from Tony G and Partners. We're a firm of consulting civil, structural and geotechnical engineers in the UK. And our paper is entitled An Industry Perspective on Geotechnical Engineering Education and a Learning Approach by Tony G and Partners. So the inspiration for the paper, we noticed the conference advertised, and one of the areas we're really focusing on is the importance of continually educating ourselves and our colleagues. And I wrote to the TC 306 committee, and they said a paper would be welcomed. So yeah, it's an important area of how we keep educating our practitioners and how we pass on research knowledge. As you all know, in recent years, the field of geotechnics has expanded due to, for example, sustainability and carbon considerations, expansion of numerical modelling capabilities, automation, data capture and AI, risk and resilience, and the emergence and growth of new fields, for instance, offshore wind, geothermal applications, tailing dams, and there are many others. So amidst this broad field, we're finding there's a lot of focus on technical expertise as focus shifts to other professional activities. And it's hard for early career engineers to understand their competency as a geotechnical engineer. Also, in the UK, many people don't undertake a specialist geotechnical MSc. BN, and that's a 3-year course, and the 4-year MN courses, they vary on geotechnical content. People enter industry with different levels of geotechnical knowledge, and even if you have done an MSc, if you're not using it, the information can be forgotten. So within industry, we need to make sure our engineers retain and develop their geotechnical understanding amidst this broad field, and we also need to keep pace with ongoing research and new findings. The ISS, MGE, and our many other professional and research organisations work hard to connect people and address key gaps in our understanding. But there's not actually an overarching strategy which would be helpful. So to address these points, Tony G have introduced our Geotechnics Academy. Other practitioners are adopting similar measures. And finally, some suggestions are made for helpful measures to support industry and academia going forwards. So just firstly, just to give an example of, we hadn't seen this, so we thought it was worth compiling a list of at least some of the groups in the UK that are involved in education and research. So here's a list of 18 groups and efforts listed for the paper, and there are more than this. For instance, the British Tunnelling Society and the British Dam Society and others. But anyway, you can see that there's a list of professional bodies, academic bodies, industry journals and magazines, and other industry organisations, for instance, several of our geotechnical laboratories in the UK are doing tours of their facilities to help developing engineers understand what really happens in practice in laboratory testing. So, Tony G, Geotechnics Academy, what's it about? So, the aims are to encompass the diverse range of skills of a geotechnical engineer, to facilitate access to corresponding guidance and information and resources and to knowledge within our company, to stimulate technical learning and discussion and professional development, to merge our experience, research and development, and to identify gaps in training and experience to enable the company to work more effectively. So just as an illustration, we're attempted to show how maintaining a strong core geotechnical design skills not only strengthens our core geotechnical design and construction practice, those areas, but also enables our engineers to be versatile and to move around our more specialist areas. And finally, we did do a survey to understand what our staff think of this. And you can see that we have a high score on increasing geotechnical understanding amongst staff, a high score on being able to use the material and the learning in their day-to-day jobs, a high score on valuing the geotechnical discussions that we have in our academy, and a high score on improving team support as a result of this collective learning. So what are the components of our Tony G Geotechnics Academy? So if you open up our SharePoint, you will see this come up on a page. So we have six areas. So we have an area for topic sessions, and these are learning and discussion sessions covering core geotechnical understanding. We have a section on literature review where we store group study of papers and webinars. We have an area for knowledge sharing, which is about internal and external and internal company project experience presentations. Then we have an area for our developing engineers prior to chartership, where they can store debate sessions towards their Institution of Civil Engineers chartership. We have an area for research and development with a list of our Tony G research and development initiatives and input. And we have an area for geotechnical learning objectives, where we've attempted to define the core skills of a geotechnical engineer prior to them getting chartered. So first of all, these geotechnical learning objectives in the right-hand corner. So these are intended to help our developing engineers gauge their experience amidst this broad field. Thank you. Gauge their experience and development as a geotechnical engineer. So we've grouped these learning objectives into 3 areas, which are site investigation and desk study, geotechnical design and implementation, and construction supervision. So just an example of one of the areas under section 2, you can see this is under geotechnical design core skills. So you can see we cover topics of like shallow foundations, pile foundations, pile group analysis, gravity earth retaining structures, embedded retaining walls, and so on. And we asked them to mark off their progress through knowledge and experience and ability. And we give an idea of what sort of level of experience we would expect prior to chartership. So then we come on to the topics for the learning and the discussion sessions. So these sessions are all centred really around the principles of John Berland's soil mechanics or geotechnical triangle. I'm not going to go through this whole list, but you can see that we've covered subjects associated with ground profile, with the geological processes, ground exploration and description. We go through a series of topics associated with soil behaviour, measurement, lab and field testing and observation. We have geotechnical design topics which split up into geotechnical design model and design processes are more empirical or semi-empirical based, but there's a lot of overlap clearly between these two areas. And finally, we talk about geotechnical design criteria and validations, such as the Eurocodes, sustainability issues, and we talk about monitoring. So these sessions are held online and in person. We gather in a group. We record all the sessions, and we save the presentations, the recordings, and the literature in dedicated areas on the SharePoint site. And there's an example, since Marina was keen to see this, of the sort of list of topics and references under all the topics associated with axially loaded piles in the appendix to our paper. So since we wanted to contribute and not at all in any way critical, we've sort of concluded the paper with some suggestions for the way forward. So efforts on research and education in industry are enabled through profits and commitments from staff. So it's generally a challenge to support a major programme of in-house learning. Therefore, could universities run programmes of fundamental learning culminating in dissemination of recent advances to help us maintain our core skills, but also to keep pace with ongoing research? So in turn, you know, the industry builds up a lot of practical experience and knowledge that goes beyond university levels. So, you know, we can support universities through guest lectures, mentoring, industrial experience or placements, and I know a lot of this happens already. But with the advent of Teams and Zoom, you know, participation need not be in person. So secondly, a proposed addition to undergraduate courses, because of the breadth of our field, you know, and the many different disciplines that are now interconnected, it would be, you know, possibly could help students to understand the breadth of the industry they're entering and the overlap of the different disciplines, and definitely the industry can help on this. So third, as we know, collaboration helps industry to influence academic research, so it addresses project need challenges. And just to bear in mind that whilst a lot of amazing work is going on in developing fantastic numerical modelling, often in the industry we're stuck with very basic soil parameters with very limited GI with which to do our numerical modelling. Would it be useful to have a review of course content driven by an industry consultation exercise? For instance, this is something I believe quite strongly in, is that a good addition to undergraduate courses would be instrumentation and monitoring. It's not yet in the UK, but possibly it is abroad. A key point is that practitioners are not able to attend conferences frequently, so there's a potential need for conferences to be more coordinated and dissemination of output to be improved if possible. And PhDs and dissertations, you know, they need to reach industry. We often realise someone's got a PhD, but it never became used in the workplace. And there's much great work from the past which must not be lost. For instance, BRE, NGI, LCPC, DGI, all our amazing research organisations. More people need to know about the ISS MGA Heritage Time Capsule Project and GeoWorld. And some form of live activity map could help all interested parties understand what each is doing in disseminating ongoing research and development. So finally, concluded remarks. The paper identifies and suggests the following advances to develop the geotechnical profession. Provide a structured learning path for geotechnical engineers to develop in their careers. Provide a roadmap linking the effects of industry and academic organisations in promoting and advancing knowledge in the industry. Collaboration on the challenges faced by industry and ongoing education. Help to facilitate dissemination of academic research into industry. An industry consultation on academic course contents. And prepare students for the breadth of the industry and the crossover with different disciplines. And thank you to TC 306 for accepting our paper, and thanks everyone for listening. Thank you.
Thank you very much. So now we're going to be moving from industry education to geotechnical engineering discipline to K-12 STEM teachers for professional development.
Well, good afternoon, everybody. My name is Ho Young-seo from Texas State University, and this afternoon, I would like to present a case study about introducing geotechnical engineering to K-12 STEM teachers for the professional development. So K-12 is public education system from kindergarten to 12th grade in the United States. Just like all of us in this room, I love geotechnical engineering and I'm passionate about our discipline. So over the years, I've led many outreach activities for middle school and high school students. And then the problem is you can only influence students, limited number of students at a time. And then I soon realized perhaps the better approach is educating their teachers about geotechnical engineering. In fact, according to a literature review performed by these researchers, teachers also do need kind of learning modules so that they can use in their classroom without much preparation. Just like all of us, they also don't have a lot of time to prepare these materials. So I thought, okay, so geotech, you know, our discipline is best discipline because we are dealing with perhaps the two most common materials on Earth, soil and water. So we developed three learning modules for K-12 STEM teachers and then introduced these learning modules through two activities. The first activity is a professional development workshop for in-service teachers who are teaching this subject in their classroom. And then the second activity is we introduced these modules to undergraduate students in College of Education, specifically Department of Teacher Education. So those are the two professional development activity that we performed in this study. So when we developed these modules, we relied on three principles. The first principle, obviously, the module that we developed should be closely aligned with their curriculum in their classroom. And then the second principle that we followed was we wanted to make sure each module have some sort of hands-on activities or demonstration activities that they can use in their classroom. And then the third principle that we followed was we want to make sure they know the real-world application of these learning modules. So the first learning module that I introduced is about friction angle. So in that module, we briefly go over the concept of static friction and kinetic friction. And then we review with teachers about the static resistance is proportional to applied normal force through the static coefficient of friction. And then as a part of the demonstration activities, participants asked to come forward and then they actually measure static friction using this activity. So I bought this digital luxury scale online and then brought a couple of dumbbells and then flat object cutting board. And then participants, they actually measure the weight of dumbbells and flat object and then using digital luggage scale, they actually measure frictional resistance. And then they repeat this activity 3 times and then they enter these values into a spreadsheet program and then they perform regression analysis and then determine the friction coefficient and then convert that into angle and then I introduce that angle. We name them as friction angle and then we introduce the direct shear test to the participating teachers and then emphasize the relevance between the two objects. And then as part of the real-life applications, I introduced deep foundation, specifically shaft capacity, so they can see the relevance between the activities that they performed and then the concept of shaft capacity mechanism. So that is the first activity. Then the second learning module is about slope stability. So in high school physics, they cover object on an inclined plane. So with teachers, we go over the basic vector decomposition, things like that. And then I introduced factor of safety concept to teachers. So mg sine theta, that's driving force, and then the F max, that's the resisting force, and then the ratio of 2 is defined as factor of safety. And then if factor of safety is greater than 1, then object slides down. If it's less than 1, it stays. And then we do this type of activity. So with a 3-ring binder and a cup initially filled with water, participants are asked to come forward, and then they put the cup filled with water on top of the ring binder, and then they let it go, and then it slides down, and then we talk about, okay, so apparently this case factor of safety is greater than 1 because the driving force is greater than resisting force, and then we pour out the water from the cup, and then now it's empty cup, and then I kind of tricked them by saying them, now the cup is lighter, so what do you think? If we let this cup go, would it still slide down, or would it stay on rest? And some people say it will still slide down. Some people say it will not this time. But when actually we let that go, it slides down. And then I revisit that equation, factor of safety equation, and then replace F max with mu s, static coefficient friction, with mg cosine theta, and then eventually that equation, factor of safety equation, just turns into the ratio of friction angle, and then the angle of inclined plane. So, and then I introduce this roadway cut slope problem as a real-life application. Many of them don't know that we designed this type of thing. One of the teachers told me that, oh, I didn't know that you cut that slope at a certain angle. I thought you guys are just excavating the dirt or whatever. So they are surprised by the fact that we do design this type of structure. And then the third module that we developed, one is more toward mathematics teacher rather than science teachers. So sometimes they use power function, logarithmic function, and then they know certain application, and I wanted to introduce the application of logarithmic function to particle size distribution curve. So we briefly introduce sieve analysis, and then I give this data sheet from one of the textbook, and then they calculate percent passing, and also I provide some guidance. And then I ask them to plot the result of this sieve analysis on two separate graphing template. One is a natural scale, and then the other one is a semi-logarithmic scale. And then obviously they will struggle to plot particle size distribution curve on a natural scale, but it's a lot more effective in the logarithmic scale. And then I ask to determine the D size, in this case D20, and then it's very difficult to determine D20 from natural scale plot than the semi-logarithmic scale. And then I'll also direct their attention to the graph template itself, and then I emphasize the major grid line, the distance between the two, they are the same because it's basically difference, but the major grid line on the semi-logarithmic scale, it's not the difference. Now it's now ratio, and then kind of present the perspective on particle size of soil, how they differ a lot in terms of particle size. So that's the three modules that we developed in this study. And as I said, these modules were introduced, the professional development workshop. So there were 12 participants, sorry about that. And 11 of them were STEM teachers, grade 6 through 12, and then one gifted education teacher. And we asked a very specific question: do you think this content is very well aligned with your curriculum? And all of them, they said yes. And then some of the feedback from the participants were like, I got great ideas to take back classroom, and I think this content could be used across multiple content area. So there were a lot of positive feedbacks. And then the second participants were, again, college of education undergraduate students, and then the course that they were taking is integrated mathematics and science method. And then there were 8 mathematics teachers and then 4 science teachers. They are not teachers yet, they are pre-service teachers, but after graduation they will be teachers. But again, these pre-service teachers also, they indicated this content is very well aligned with the content that they'll be teaching after graduation. So all in all, I think I made it pretty quick in the interest of time for all of us. So the conclusion, I think this case study was well received by K-12 teachers, And going forward, I'm planning to develop more modules like this so that the younger generations, they can see the world through the lens of geotechnical engineering. So thank you very much.
Thank you very much. So in the interest of time, we have 2 presentations left, and I know we need a certain amount of time to get to dinner, so we're going to just keep going, save your questions for dinner. So next, we're going to talk about game development-based learning curriculum module for an undergraduate soil mechanics geotechnical engineering classes.
Well, good afternoon, everyone. My name is Bina Ajmera. I'm an assistant professor at Iowa State University, and I'm going to be talking about some of the work that my colleagues, Cassandra Rutherford, Alinka Poplin, and Alyssa Emery, and I have done with 2 graduate students from the School of Education, Justin Sabrowski and Paul Chung. We are looking at game development-based learning curriculum modules for our undergraduate soil mechanics course. Earlier today, we talked about game-based learning, and there's a slight difference between the 2 of them. So very quickly, I'm going to just introduce what is that difference between the 2 of them, talk about how we implemented this in our classrooms, and specifically focusing on the video lectures and the activity worksheets that we created, as well as the grading rubrics. I'm going to give a few examples of the games that our students ended up developing, and then talk very briefly about the implementation outcomes. Those are in 2 of our other publications, so they will not be the focus of this presentation. And then just summarize with what we learned. So as we've heard throughout the day, there's been a rapid shift to online and hybrid teaching methods when the pandemic hit, and as a result, it caused many disruptions to the way we traditionally teach and the way students traditionally learn in the classroom. This ensured that our shifts ensured that we had a continuity of the instruction, but it did lead to a lot of negative impacts around student engagement, their learning outcomes, teamwork dynamics, and the professional skills that we're developing. And professional skills are often referred to as soft skills, or the teamwork, communication, etc. So. Now, today we're back to in-person classes for the most part, but we've noticed that classroom attendance and student engagement still remains low, and that's what we're trying to address through our game development-based learning methods. So we thought this was a promising strategy in order to foster student engagement, enhance creativity, and strengthen both technical and professional competencies. And it's a combination of game-based learning and the constructivist theory. So in game-based learning, gaming elements are introduced in the classroom in order for us to try to enhance the cognitive skills, the motivation, and interactions among the students. The constructivist theory states that students gain more when they actively create their own educational tools instead of when we give them the educational tools. And so we're merging these 2 together in order to have them create their own games that help them and their classmates learn. And so gaming in general has been shown to increase retention, motivation, cognitive abilities, while giving them an opportunity to experiment and develop an understanding of the material. We also know it gives them immediate feedback. It reinforces their student persistence, it reinforces their achievement because they know right then what they did wrong, what they didn't do, what they could learn from that experience. So we're hoping that this curriculum will integrate the active learning strategies associated with gaming with having them build their own educational tools. So the students were put into teams asked to design, prototype, and refine an educational game based on a core geotechnical engineering concept. And they could pick whatever topic they wanted to work on from the duration of the semester. Our goal was to try to use that game as a way to improve the technical knowledge of the students that were involved, as well as their professional skills and attitudes by having them get engaged in the learning process. And we had 3 empirical questions that motivated this work. I'm not going to be focusing on the results, but the questions were focused around learning outcomes, the professional skills that they develop, and the motivation and engagement associated with participating in this type of a pedagogical approach. And like I said, the results from each of these questions have been summarized in some of our other papers. I wanted to use this opportunity to talk a little bit more about the instructional approach and how we did that, which we couldn't talk about in some of the other locations that we published. So to talk a little bit about the curriculum itself, it was designed using the principles of universal design of learning, which says that we want to have the students engage with the materials in multiple different methods. We implemented the curriculum module in our undergraduate soil mechanics class, which is taken by 3rd and 4th year students in a 4-year degree program. And the implementation occurred over 3 semesters. Each semester we had about 5 or 6 sections of the course, each with approximately 20 students in it. And then during that time, the course was taught by 5 different instructors. So we had 4 of the full-time geotechnical faculty at our institution teach it, and then we had a doctoral candidate who was gaining some teaching experience teach it in one of the implementations. As part of the curriculum, the students worked through the process of developing a playable prototype of a serious geotechnical engineering game. And for those of you that are not familiar, the idea of a serious game is that it's more for learning and teaching and less for the enjoyment and the fun of playing a game. So it has a learning component to it. Now, students have no idea how to create a game, especially students in our geotechnical engineering classes. So we tried to remedy this by providing some videos that were developed by Alinka, who is a professor in the game design major at our university, that talked about how games are designed, what are the associated mechanics, how do you select different game types, when are they effective, and so on, and then what are the elements associated with the gaming. And at the end of the semester, the students had to turn in their game, and they had to deliver a presentation that talked about the key aspects of the game as it related to those videos and the concepts that were taught. And we thought we would have a lot of fun at the end by having all the students play all the games that were developed in the sections. And so our review session for the class was playing the games that were developed amongst all of the teams. So we built this into our existing curriculum. Nothing was removed out of our undergraduate soil mechanics class. This was added into it. This kind of shows the activities that we had in the first 6 weeks where we were trying to put more emphasis on learning the game mechanics. You'll notice that there's a series of places that says videos associated with it, which I'll come back to in just a little bit. The second half of the semester focused on giving them time to build their prototypes, to work in teams, to develop that, and to figure out how they were going to assess that their game actually helped the player learn the concept that they were trying to teach. And week 16 is our finals week, so we didn't have any actual lab activities in that week. So we played these the week beforehand, where it was our review session once again. So the videos, we assign them as part of the pre-laboratory assignments that we have every week for our class. They ranged in topics, so this is the list of the videos and how long they were. They typically ranged from about 8 minutes to the longest one being about 25 minutes. On average, they spent about 15 minutes or so watching the videos. And then, since those were individual assignments, we realized we needed to build in some more teamwork for them because they would watch the videos and forget about them. So we ended up adding some activity worksheets into the lab session to build some of that team interaction. So the worksheets, I'm going to summarize them really, really quickly. The first one was kind of just getting an introduction into the team, making them start talking about the types of games they like, why and why not. And then we started connecting those games with some of the contents in the video. So defining what is a game versus what is playing, how they differ, and classifying the games based off of the formal definitions that are available, describing the elements that are associated in their favorite games. So this was kind of to just get them thinking about how they would design their own game. And then that led to a brainstorming session where they had to create a mind map that talked about all the formal and dramatic elements that they would incorporate into their game. Number 6 is intentionally missing. We'll come back to that one in just a little bit. But the 7th worksheet is on designing the questionnaire that assesses whether or not they were successful in the outcomes of their game, and then ultimately they had to come back and describe what was the game, what are the rules, how do you play it, and so on. Now, number 6 was actually added afterwards, and I should also add that the worksheets were added after the first implementation where students, being students, decided to wait until the very last minute to build their game, and they didn't talk to each other, and they just threw something together to finish the project. The second time around, we saw that they were dismissing ideas because they didn't like them for whatever reason. So we had a reverse brainstorming session. We gave them 6 scenarios, and we asked them to come up with solutions for these. The idea was that they were impossible problems, and that they had 5 minutes to brainstorm these ideas before coming together as a team to discuss, refine, and then present out those ideas to show them that there is no such thing as a bad idea. It just may need to get flushed out in a different way. So with that, I'm running out of time here, so I'm going to go very quickly. None of the other assignments were graded. The only item that we graded was the final presentation, which we allowed the instructor to grade in whatever mechanism that they seemed. We just really wanted them to participate in the gaming activities. So they developed all sorts of games. Those are some of those games. And of course, we had to bring in our structural engineering department chair and have him get questioned on the gaming process with our administrative assistant. So they did a pretty good job in stumping him with some of the questions. So just in general, we found that the results were really positive. There was an increase in communication and problem-solving skills. There was no statistical increase in enjoyment, but there were some other connections to motivation that we saw from participating in those activities. And there were a series of limitations, which I will not go into in our implementations, but they are discussed in the paper. And with that, I will just conclude here with some of the things that we could find and acknowledge the many sponsors that made this possible. So, thank you.
Thank you very much. So we have one more presentation before dinner, teaching soil mechanics in a changing world.
So, hello everybody. Thank you for staying here until the last presentations. So, yeah, I'm going to talk about how to teach and what to teach soil mechanics in a changing world. Soil mechanics has been, as I say, if we consider that it started by the concept of tertiaries 100 years ago. So do we still need to continue to teach this concept, or what need to change? This is our motivation to for this presentation. I would like to share our experience at École des Ponts in Paris on the class of soil mechanics. So yeah, just to get back in the context. So we have seen during 2 days, we talk about climate change a lot. So now engineers, geotechnical engineers should not only consider stress, water, but start to talk about uncharted soils and others, also vegetation or even frozen soils, soil storing, everything. So this is the first thing, and also big data. We have new technologies now. We start to have a lot of data. Just an Excel table cannot put everything inside this. And how to deal with this? We talk about AI tools that is changing how students learn everything, and how we teach also. Numerical tools also. Tomorrow we have half a day talking about how numerical tools can change the life of geotechnical engineers. And also another thing is that the new generation of students, I think they are changing. It's not the same students that we have 10 years ago, 20 years ago. So how we can adapt the teaching of soil mechanics with our basic concept were established in the 20th centuries, and now to have the new generation of geotechnical engineers to prepare for the future challenge. This is what we try to think about this. And if you have a look about the literature review on teaching and soil mechanics, we see this geotechnical engineering to say that, in fact, geotechnical engineering is I think it's very empirical domains. That means most of our concept is very based on the measurement on the fields, and this exists like that. And sometimes I think we forgot to explain to the new to the students that why we choose this correlation. This morning we talk about correlations. We have a lot of correlations and this. And now within this experience that traditional that we have now, we have different point for big data changing how we monitor the ground. Numerical tunes and AI tune is changing how we use the model, and also the climate change is changing how the solicitation will impact the structures. And yes, it's also we talk about the critical state soil mechanics, and there are also the notion of now we are try to associate geotechnical challenges with energy and the environment. So this is also another big challenge that we start to talk about temperature, heat for geotechnical engineering also, and other concepts inside. We go further in the stress range, not only a few centimeter, a few 100 kilopascal in the stress range also. And there are some papers discussed about between education and training, what we teach and what we need to, what students need to practice. So yeah, so now I'm trying to share what we teach in École Nationale des Ponts Chaussées, in the Department of Civil Engineering and Constructions. So just a quick explanation of the French system is quite complex. I don't know. So this is a standard system here. After the high school, we have the 5-year, 3-year bachelor's and 2-year master. So this is European systems. But in France, we still have very good students follow this path, where they pass 2 years first in the preparatory classes outside the universities, in high school mainly. And then after that, they pass an examination and then they enter the engineer's school. So they pass 3 years in the engineer school to get, after 3 years here, the master degree, and they get at the same time diploma of engineers. So we call that the Gonze. So this is what at ENPC we have this system here. So that's why in the program at ENPC we have only 3 years. So the first year after this examination here, they enter the school and they still have 1 year to consolidate all the scientific foundation related to ENPC. So ENPC was created more than 200 years ago. It's more well known on mathematics, computer science, and also mechanics. And then they discover also new disciplines, particularly for economics and social science. So this first year for every student. And then after that, they separate in different 6 departments. So there are roughly around 80 or 90 students will choose the Department of Civil Engineering and Constructions. So the courses of soil mechanics is in the first semester of the second year, so it's the semester 3 here. So this is the first semester where they really start to learn about civil engineering, everything. So roughly we have 80 and 90 students, depending on the years, and we divide them in 3 subgroups. Each subgroup will be 1 teacher. We coordinate by 1 teacher, and usually we have 13 sessions of 2.5 hours. Each session we have 1 hour of lectures and 1.5 hours hand-on session by doing exercise, tutorials, and usually we still try to keep let's say the core session of soil mechanics, like description of soil description, phase relationships, and then we talk about mechanics like effective stress, total effective stress in soil. We talk about continuum mechanics, and then we talk about water flow is important, Darcy law and hydraulic conductivity. But I mentioned the red point here. We introduce also the porous mechanics. So this is really different from the standard soil mechanics classes. Only 2.5 hours is not enough, I'm sure, to talk about porous elasticity, rock mechanics. But the idea is that to say to the students that besides the concept of tertiary effective stress, you can use when you go higher stress range. Maybe there are another concept that you need to know. That is the idea. And after that, we talk about the consolidation. And then it's very interesting because consolidation here we start to talk about power mechanics already in the theory of consolidations. And then you can see what is the limit, what is the theory, the assumption used in soil mechanics when you use consolidation here. And then we can combine with what we talk about power mechanics here to explain it better. And then, of course, we talk about soil behavior under derivative stress. It's important. And because this is a unique mandatory classes in geotechnical engineering. Some students, after that, they will never have another classes and courses in geotechnical engineering. We try to at least talk a little bit about some application in geotechnical engineering by talking about at the ground induced by construction of the ground, returning work here. Just one lesson to have an idea of what is the real construction in geotechnical engineering. Another point that I would like to say that now, because students start to use a lot of numerical tools, so we think that it's important to have a good knowledge about constitutive model. So we spent 2 other sessions here to talk, one session to talk about the linear elastic perfectly plastic model, another session talk about the modified chemical model. Again, when I say sessions, I mean 1 hour lectures and 1.5 hours hands-on sessions and exercise. And then besides this, let's say standard traditional lectures and hands-on session, we introduced 2 projects. The first project is we call literary review project. That means we divide in group of 2 students. Each group of students will choose 1 topic. And then they will do, like during 1 month, the literary review on this topic by ChatGPT if they want. And then they will present in 5 minutes in front of the class to explain this, to have question, discussion, and they've been evaluated by the teacher and also the other student. And the topic is very wide. It can be different, can be so different topic in geotechnical engineering, like soil improvement technologies, different technique here. They can choose one of these. Geotechnical structures, different structure here, they can choose one of these. Different geotechnical phenomena, different case study which are interesting, like Tower Pisa, Teton Dam, everything. And also they can choose very new, like artificial intelligence, big data, or even other topic. Okay, I'll go quick. So the feedback is that the student really like this. Just 2.5 hours, they learn a lot of topic around geotechnical engineering. And the second project is constitutive model. So we give after learning this, we give them a set of parameters, and we ask them to model themselves by writing themselves the code or make Excel everything to reproduce the behavior of soil in traction test or rotometer test, plotting this graph like that. So this is a project they do themselves. So this is a class we have. And after that, if they want to choose the other semester, they have other classes here on geotechnical engineering. So we give the base to continue the other classes if they want later. So I will finish here. We think that this is Asian concept and soil mechanics are important. We need to maintain this. But I think you need also to introduce other limit outside this Asian concept. And constitutive model, we think is important, but we need to improve this again, because sometimes students say that they can do the project, but they are not sure they could learn something about it. And last point, we think that it's very important to have a close interaction between these classes and these courses and the other courses in geotechnical engineering to interact between these to adapt the content. Okay, thank you very much.